The last section in Chapter 7 is 7.4, distributed forces. And we have three main ways of looking at these distributed forces: a line force, a surface force, or a volume force. And we'll kind of look at line force in this section, and then I'll have another one on surface forces. But a line force essentially looks like this. I know I've shown you this train before, but it's a great example because we deal a lot with these things in bridges and in beams. So this force that we're looking at again of this train is a distributed force. It has some loading along the x-axis, if we created this as an x-axis, right? And this would be our y-axis in this direction. But there's some loading that goes along with it, and we can then create that and find a similar system, an equivalent force system, which is just a single force. And then we can really analyze it looking at it from a statics point of view. So if we have the equation for our distributed load, this is this script lowercase w. It has if we have an equation for it in terms of x as it moves along the length of the beam, we can use that and integrate that whole distributed load to find essentially the area under the curve, which really is equal to our force. So if we want to find where to locate and put this force F, we need to find this x bar value. And we can look at this x tilde again and integrate this equation, and then find out that location. Again, we'll have a formula for integration, and also we can do it in terms of composite shapes if we have some distributed load that is in terms of a composite shape. Another thing I want to point out is the coordinate system. 90+% of the problems that we do, our coordinate system will be located in the lower left or the left-hand side of our beam, and then the positive x will go along in that direction. For, I would say, 90% of the problems that we do. So just a few quick comments about our distributed loads. If we have beams with a distributed loading, it's really important, if we can, find an expression of this distributed loading in terms of x. There are some values of doing that. And one of them is if we know that in terms of x, we can then determine our internal forces in terms of x for our shear force and our bending moment throughout the whole length of the beam. And that's what we'll be covering in the very next chapter. So this method that we're going through right now is very important to know for Chapter 8. The other advantage of knowing this, if we know it in terms of x, is that we can find our deflections, stresses, and strains throughout the whole length of the beam and our deformation of the beam, and that we will be doing in the next class of mechanics of materials. So this material is used in other classes, so we need to be able to find these distributed loads in terms of x. Okay, so I'm going to run through this example down below in finding the support reactions and finding a distributed load, the function for that distributed load. Okay?